If the universe is slowing down in its expansion, then we expect a certain relationship between the distance and the redshift of objects, simply because more distant objects are probing a earlier time in the universe when the expansion rate was presumably greater than it is today. The surprising discovery was that the supernovae were even fainter than expected, and that implied that the universe's expansion rate was not slowing down, but actually was speeding up. And that led to the first really strong evidence that the expansion rate was accelerating rather than slowing down.
From the heart of The Ohio State University on the Oval, this is Voices of Excellence from the College of Arts and Sciences, with your host, David Staley. Voices focuses on the innovative work of arts and sciences faculty and staff, with departments as wide-ranging as art, astronomy, chemistry and biochemistry, physics, emergent materials, and mathematics and languages, among many others. The college always has something exciting happening. Join us to find out what's new now.
I'm pleased to welcome Paul Martini into the ASC Marketing and Communications Studio today. He is a professor of astronomy and physics at the Ohio State University College of the Arts and Sciences. He is an observational astronomer and instrumentalist with a focus on observational cosmology and the evolution of galaxies and active galactic nuclei. Dr. Martini, welcome to Voices.
It's a pleasure to be here.
I want to begin, first of all, by talking about the work that you're doing on the expansion of the universe. Now, we know that the universe is expanding, but evidently it's accelerating. And
yes,
I thought it was actually the opposite. I thought the universe was now contracting.
Our expectation is that the universe should be decelerating. That is, its expansion rate should be slowing down because of the influence of all the matter in the universe, the gravity of all objects pulling on all other objects. And so it was a huge surprise in the late 1990s that we discovered that, in fact, the universe's expansion rate was accelerating rather than decelerating. This implied that there is some aspect of the universe, some law of physics that we just don't know, that is causing the universe to literally defy gravity.
How was this discovered?
This was discovered with observations of what are called type 1a supernovae, which are a type of object that in astronomy are called standard candles, or really standardizable candles. The basic idea is that a supernova, particularly a type 1a supernova, has a relatively well-calibrated peak luminosity when it is evolving. So a supernova explosion is a star that explodes and releases an enormous amount of light. And like a lot of things that explode, it gets brighter and then it gets fainter again. And with supernovae, we can measure the evolution of their light over time. And for type 1a supernovae, that information tells us what the intrinsic luminosity of the supernova was. And if we can compare that intrinsic luminosity to its observed flux, we can derive how far away the object was.
And so by looking at these sorts of objects, we've been able to discern that the universe is in fact accelerating.
That's right. The big challenge in understanding the evolutionary history of the universe is understanding how to accurately measure both distances and redshifts to objects. The redshift part is relatively easy to measure because we can measure spectroscopically how fast something is moving away from us. And all objects outside of our local universe are what are called redshifted, meaning that they are moving away from us.
And we can see that like on a color spectrum, right?
That's right.
Yeah.
That's right. And that's relatively straightforward to record with modern spectrographs. The distance part, however, is really challenging to measure because objects in the universe are at such enormous distances that the common ways that we determine distance, such as looking at a map or bouncing radar signals off of objects, are simply impossible to use because the objects are so far away. And by far away, I mean millions of light years away. That is literally the distance that light travels in millions of years. The closest galaxy, like our own, to the Milky Way is the Andromeda Galaxy, and it's at a distance of about 2.5 million light years. And all the objects that I study and the objects that we study to measure the expansion rate of the universe are many hundreds, if not thousands of times farther away than that. So we're talking about millions to billions of light years away.
What you're hearing in my response is awe, I think, at the immensity of this.
The scales are amazing. So we use supernova explosions to measure the expansion history of the universe because distances are very challenging to measure in astronomy because the objects are so far away. That's why we use objects like Type 1a supernovae as standard candles. The really amazing observation that was made first in the late 1990s was that distant supernovae were even fainter in their appearance than we expected. The expectation was that more distant objects will be moving away from us more rapidly than nearby objects because of the expansion of the universe. However, we expect that if the universe is slowing down in its expansion, then we expect a certain relationship between the distance and the redshift of objects, simply because more distant objects are probing a earlier time in the universe when the expansion rate was presumably greater than it is today. The surprising discovery was that the supernovae were even fainter than expected, and that implied that the universe's expansion rate was not slowing down, but actually was speeding up. And that led to the first really strong evidence that the expansion history or the expansion rate was accelerating rather than slowing down.
And you talked about just the mass in the universe. What's causing this expansion? We knew what was happening. What's different now, or what have we learned?
The accelerating expansion of the universe is a huge puzzle. It is commonly ascribed to something that's called dark energy. And
Do you ascribe it to dark energy?
I like the name. However, an important part about the term dark energy is that it's really a great name for something, but it is not a description of what is physically happening.
You're going to have to unpack that for me.
Dark energy is a term that was coined originally by Michael Turner, an astrophysicist at the University of Chicago, to explain the accelerating expansion of the universe. However, we can name something, but that doesn't necessarily mean that we understand how it works. A good way to think of dark energy as a property of space-time itself, or it's potentially a property of space-time itself, that is exerting a negative pressure on the universe. And as the universe expands and gets larger, the universe has more and more volume, and therefore there's more and more of this negative pressure, and that causes the expansion rate to continue to get greater and greater over time.
So this has been theorized, not actually observed. Is that a fair statement?
It is true that the accelerating expansion of the universe has been well observed. However, the existence of any negative pressure associated with the vacuum of space has not been observed. This is just a hypothesis that could explain it.
You're being very gentle and diplomatic. So how do you feel about dark energy?
Well, I love the term because it sounds really cool. Another term that people use a lot in this field is the concept of a cosmological constant. Mm-hmm. And a cosmological constant is one potential explanation for dark energy, but just like the term dark energy, it is really a mathematical description rather than a fundamental physical relationship. The cosmological constant is a concept I think a lot of people have heard of. It was something that was originally introduced by Albert Einstein shortly after he developed his theory of general relativity. And at the time, astronomers thought that the universe was actually static. They did not think that it was expanding or contracting. This was well before we had the concept of the Big Bang, for example. Mm-hmm. And Albert Einstein realized that gravity should cause the universe to contract. And if the universe was static, there must be something that's keeping it from contracting. And so he introduced a cosmological constant into his theory to explain the observations. And only a decade or so later, Edwin Hubble put together redshift information and distance information for galaxies and showed that actually the universe was expanding. And that led Einstein to famously call the cosmological constant his biggest blunder. And it was thrown out from cosmological modeling until basically the late 1990s, when it suddenly became necessary to explain the accelerating expansion.
Necessary because?
Necessary because the accelerating expansion couldn't be explained by the gravitational forces alone. It was in contrast to the gravitational forces. And so we needed some way of explaining, or at least creating a model to explain the observations, to match the observations. And a cosmological constant is a simple way to adjust the general theory of relativity to allow for the accelerating expansion of the universe.
I introduced you as an observational astronomer. And obviously, if you're going to do observations, you need technology. You need telescopes and things like this. Has this new understanding been influenced at all by technology or by new technologies or better measurement instruments?
Absolutely. The field that I work in, observational cosmology, is hugely driven by technology. And I work a lot on the technology developments that is enabling us to collect more and more information about the universe. We're really in what is called an era of precision cosmology, where we are making better and better measurements of the expansion history. And that will allow us to ultimately determine whether or not the expansion rate of the universe is consistent with a cosmological constant, or if instead something that is another really exciting possibility is that the dark energy component is perhaps changing over the history of the universe. And that might indicate that it's some other force of nature or some other energy field that is different from a property of just space-time itself, as suggested by the cosmological constant idea.
So you are part of the Dark Energy Spectroscopic Instrument collaboration. Could you tell us a little bit about this?
Yes, the Dark Energy Spectroscopic Instrument collaboration, or DESI collaboration.
DESI, yes.
It's an international collaboration of hundreds of scientists that are working to measure the expansion history of the universe with exquisite precision. We have built a spectrograph that is located at the Kitt Peak National Observatory near Tucson, Arizona. And this spectrograph is capable of observing 5,000 spectra at a time. And with it, we are conducting what is already the largest spectroscopic survey of the night sky that's ever been obtained. And not just the largest, but the largest by an order of magnitude at this point. So more than a factor of 10 larger than any previous survey. And what we're specifically doing is we are measuring the redshifts for millions and millions of galaxies. Actually, we've just recently crossed the threshold of having observed 50 million objects.
Wow.
And we've been operating our survey since May of 2021. So it's only been a few years, and we've obtained many tens of millions of observations. The goal of this is to measure distances to objects at a wide range of redshifts. However, we're using something different from supernovae to measure distances. Instead, we're measuring something called the Baryon Acoustic Oscillation Scale, or BAO scale for short. The BAO scale is what's called a standard ruler rather than a standard candle. But the idea is very similar. If you know the intrinsic size of an object and you observe it at different distances, then the angular size of that object can be used to infer how far away it is. The Baryon Acoustic Oscillation Scale is, however, a really, really large ruler. It is a ruler that is about 500 million light years across. And it's something that we observe in the distribution of galaxies in the universe, but it's an incredibly, incredibly subtle signal. And so we need millions and millions of observations to even measure it at a single distance.
You said that you were involved, you didn't claim that you were doing this yourself, but you were involved in building a spectrograph. When you say build, you mean like engineering, like constructing?
Yes. The Dark Energy Spectroscopic Instrument, the instrument itself, is a fiber-fed spectrograph at a 4-meter telescope that has 5,000 robotically positioned fiber optics cables that collect the light from individual objects, and then they connect that fiber system to 10 spectrographs that record all of the light across the whole visible spectral range, and we use those spectra to measure redshifts as well as other properties of the objects. I and my colleagues at Ohio State were part of building parts of the spectrographs as well as a number of other components that make the DESI instrument possible. But we were part also of a larger collaboration. The DESI experiment is led at the Lawrence Berkeley National Laboratory in California, and it includes partners around the world, such as from France and Spain and the UK, in addition to the United States. And many scientists, probably 100 scientists and engineers, contributed to the construction of the DESI instrumentation over the course of many years.
It just always amazes me. Is this true of all astronomers, that you sort of make your own tools, make your own technology?
It is fairly common. The commercially available technology for detectors, for spectrographs, for even telescopes is valuable for certain types of research that we do. But the vast majority of astronomers use what I would call bespoke instrumentation. And generally, this is built by instrumentation groups at universities or at national labs or at observatories. Our instrumentation group at the Department of Astronomy is one such group, and we build custom instrumentation that can solve specific scientific questions.
I know that you're working specifically on the Lyman alpha forest, and you have to explain to me what this is.
The Lyman alpha forest is a phenomenon that we observe in the spectra of distant quasars. So first, a quasar is an object at an incredible distance that has a supermassive black hole in it that is accreting a lot of matter from the surrounding galaxy in which it resides. That produces an enormous amount of luminosity, and thus quasars can be observed across almost all of the known universe because they're so luminous. We use these very luminous quasars to effectively backlight the intergalactic medium, which is the space between galaxies. The vast majority of the universe is nearly empty, but it does have regions where there is more or less gas, and that gas is mostly hydrogen, and some of it is neutral hydrogen, meaning that it has a bound electron, and that bound electron can undergo transitions when it absorbs radiation. And the Lyman alpha forest is a measurement of the neutral hydrogen gas that is between us and a very, very distant quasar. The great thing about the Lyman alpha forest is that we can measure the matter distribution along the line of sight to the object, and we get lots of information about how the matter distribution in the universe changes when we observe even a single quasar. Whereas normally, or at least at lower redshifts, what we primarily do is we measure the distribution of individual galaxies, and we use basically each observation of a galaxy as one measurement of the matter distribution. Instead, for the Lyman alpha forest, we're measuring the matter distribution along the entire sightline, and so we get a lot more information from each observation.
So has the DESI collaboration yielded any answers to this question about the expanding, the accelerating universe?
Yes, we had some very exciting results that we presented in April of this year, and then some more results that came out just last month in November. The observations that we published and the analysis that we published this year is based upon our first year of data collection. So this is data that we collected from 2021 through 2022. And since it's now 2024, that gives you a sense that it takes a while to do the analysis. These observations, however, and the analysis led to some really exciting results. We have the best measurement to date of the expansion history of the universe, especially when we combine with other projects. What I am most excited about is that we see some very slight or tentative evidence that the accelerating expansion of the universe might not be consistent with a cosmological constant. We see a really exciting result. However, I don't want to oversell it because the statistical significance of it is not in the category that most scientists would consider overwhelming.
Okay.
Or definitely true. In astronomy and in physics, a lot of the time we talk about whether or not something is a result of 3 sigma significance, which basically, in principle, statistically means that it has a 99% probability of being true. However, in the astronomy community, we joke and we say that about half of such results end up being incorrect. So that's why I don't want to oversell the result.
Yeah.
But it does get me really excited to see what results we will have with our next analysis.
What's exciting you?
Well, at this point, we now have over 3 years of observations, and we have many, many times more data, and therefore we should have much, much better statistical precision than we had in our papers describing the year 1 results. So I am very excited about whether or not this interesting result from this year will be confirmed with much more data or if it will go away. And I'm really excited to see what the answer will be.
You know, as you've been talking, I'm really struck. You talk about forests and candles and rulers. I'm really struck by the analogies that astronomers seem to draw. This is commonplace in your field?
I would say so. I haven't thought about it in those terms, but it's a nice way of describing what we're doing more broadly. Rulers and candles are easier to grasp, and I think even for professionals than things like the distance that sound waves traveled in the early universe before recombination. I mean, that's just much more of a mouthful as well.
And so you use this professionally. It's not just with novices or amateurs like me that you use this terminology.
Yes, we use these terms also professionally. We definitely use terms like standardizable candles and standard rulers, although we also will talk about the BAO scale.
Right. Tell me some of the classes that you teach, both undergraduate and graduate classes.
One of the classes that I've taught a number of times is a class on observations of astronomical systems. This is a graduate course that covers all of observational astronomy, ranging from the sun and the solar system to exoplanets and stars to galaxies to distant quasars. And that's a fun class, although it's somewhat of a class where I feel like the students are drinking from a fire hose because there's just so much content. Another class that I've taught and I really enjoy is a class on advanced data analysis that I just developed in the last year. This is a course that's aimed at upper-level astronomy and physics majors and is designed to introduce a lot of the concepts in data science and machine learning that we use in modern astronomy and in research more broadly. And it's a course that a lot of our majors like to take because a lot of them are interested in graduate study and research where they will be using these tools, but it's also something that prepares them well for other careers outside of astronomy and astrophysics.
How's machine learning being used in astronomy?
Astronomy is very much a field of big data. It is even perhaps one of the first fields that had enormous quantities of data, dating back over 100 years ago with the first photographic projects that mapped the entire sky. In the DESI project, I mentioned that we have observed over 50 million spectra already, and each one of those spectra has many thousands of pixels of information that are recording how bright a given object was at each wavelength or at each range in color that we observe. In addition, we collect a lot of other information about objects like their position on the sky, that in particular, but also their photometric properties. And we use all of these data and combine them in different ways and for information about their physical properties as part of our analysis. And so having data analysis tools that can process this incredible volume is really very valuable.
I'm curious to know why you're an astronomer. Did you know when you were 4 or 5 years old that you were going to be an astronomer? Or was this something that came later in life?
I've wanted to be an astronomer since I realized that this was a career path. I've always been fascinated by really big questions like where do we come from? Where did the universe come from? Or what's going to happen in the history, or what's going to happen in the future of the universe? And then once I started learning about space and realizing that there were objects in space like black holes or neutron stars where a single teaspoon has the same mass as Mount Everest, or that there are planets in the universe that have surfaces of all lava or maybe all water or atmospheres of methane. That just got me so excited about the incredible diversity of the universe and the really bizarre physical conditions that were actually real, but are so far beyond my experience in my everyday life on Earth. And it just got me so fascinated that I was hooked, and I just wanted to keep learning more.
Why this particular problem of the accelerating universe? How did you alight on that particular problem of all the problems you could have been examining?
It's something I really stumbled into in the last 10 years or so. I previously had done most of my research on galaxy evolution and supermassive black holes. But I got excited about dark energy, I think going back to my roots in childhood and what got me excited about astronomy in the first place, which was trying to understand and answer, hopefully, some of the biggest questions about the universe itself. With the Dark Energy Spectroscopic Instrument, it is a great collaboration that allowed me to both pursue my interest in building instrumentation and then using that same instrumentation to explore some really fundamental questions. And fundamental questions like, why is the universe's expansion accelerating, is very difficult to explore with a relatively small group of people because the scale of the data that are necessary to make substantial progress is just really too enormous. And so working in this collaboration with people with lots of different skills, lots of different backgrounds, and working together on large projects, it's been a lot of fun for the interpersonal connection, but it's also been great to see what we can accomplish together that we couldn't have accomplished on our own.
A minute ago, you talked about questions about the future of the universe. What do we know about the future of the universe?
We can take the models that we have of the accelerating expansion of the universe and we can project them forward. One of the really remarkable results of that process is that it means that we're somewhat at a special time in the universe now, because now we can collect data on galaxies at a broad range of redshifts, and we can measure the accelerating expansion of the universe. But if we came back, or if we were still around in 100 trillion years or so, the accelerating expansion means that the galaxies that we see in the universe today would not be visible to us if we were still in the same place hundreds of trillions of years in the future. The universe would be maybe a lot less interesting looking, and we wouldn't be able to do the same kind of investigation.
Any possibility of it collapsing back on itself? Or is the sense now that it's just going to keep expanding forever?
The sense now is that it will keep expanding. For many decades, it was very much an open question whether or not the universe had enough mass in it to eventually cause the expansion rate to completely stop and then start to contract again. But with the discovery of the accelerating expansion, provided that continues, then the universe will not collapse back in on itself.
Tell us what's next for your research.
We are currently working on a proposal to the Department of Energy to conduct a successor project to DESI, which we call DESI 2. DESI 2 will observe the high redshift universe with a somewhat similar fidelity to what the DESI experiment is doing in the local universe. The DESI experiment is obtaining its most precise measurements out to distances that corresponds to the last 8 to 10 billion years of the expansion of the universe. What we would like to do with DESI 2 is we would like to obtain similar quality measurements, but even closer to the era of the Big Bang, And that will allow us to study some of the unique physical conditions that happened very early in the universe that we can't access any other way. We can't, for example, reproduce those conditions in laboratories on Earth. And so we'd like to understand the early universe with DESI 2, and then we'd also like to better map the local universe so that we can better investigate the nature of dark matter. And that will include both measurements of the matter distribution of the Milky Way galaxy, but also observations of how galaxies in the nearby universe are clustered together.
New technologies, new instruments as part of DESI 2?
DESI 2 will be mostly using the same instrumentation that we have now. However, we do plan to improve the detectors, in particular the detectors that we use to collect the bluest radiation or the bluest light. There is an interesting new technology development that produces lower noise observations, less noisy observations, and that will allow us to map the high redshift universe more efficiently.
Paul Martini, thank you.
Thank you. It's been a pleasure.
More information about the podcast and our guests can be found at go.osu.edu/voices. Produced by Doug Dengler. I'm Jen Farmer.